Today, we're going to unlock a very powerful tool in calculus called logarithmic differentiation. It's a technique that transforms even the most intimidating functions into manageable ones when we're trying to take the derivative. So, you've been dealing with some fairly complex functions, maybe a product of multiple terms or an exponent raised to another function, and they can be messy. Um, and maybe you've thought there has to be an easier way to differentiate this. Well, there is. And it's not just a shortcut, it's actually an elegant strategy that simplifies differentiation using one of math's greatest inventions, logarithms. So, you learned in the last lesson about the natural logarithm, ln, and exponents. And today we're going to build on that. And we're going to start by taking the natural logarithm of both sides of an equation. And by doing that, we can convert exponents into coefficients, allowing us to differentiate in a way that's both logical and efficient. So by the end of this lesson, you'll be able to handle functions that once seemed impossible, all while deepening your understanding of that interplay between logarithms and derivatives. So let's dive in and see how we can work smarter and not harder. Let's start by looking at an example. So how can we differentiate a function that's a variable raised to another variable? Like this example here, where we have y equals x raised to the power of x. So what's the derivative of this? What is the derivative of x raised to the power of x? We need to use the process called logarithmic differentiation. So really what we need to do is take the derivative of both sides of this function in order to be able to accomplish that. So what is that going to look like? Well, we know that x to the power of x is exponential. You learned that in the last lesson. So we are going to use the natural logarithm, or ln, to get rid of that power and make things a little easier. So we are going to start by taking the natural logarithm of both sides. So we will have ln of y is equal to ln of x to the power of x. Now remember, the whole point of writing it this way is so that we can take this power and turn it into a coefficient. So let's go ahead and do that. So we're going to take that x and not that. So I'm just going to rewrite that. So we have x, ln of x to the power of x. So let's rewrite that. Ln of y is equal to x ln of x. So now we've gotten rid of that power. So now what we're going to do now is take the derivative of both sides. So really we want to compare the derivative of dy as it relates to dx, all compared to the derivative of dx. So we're going to take the derivative of both sides. So the derivative of ln of anything, if you remember, is just 1 over that variable. So the derivative of ln y is just 1 over y, and that's still times that dy compared to dx. Then we're going to use the product rule to take the derivative of x ln x. And we can think of this as two distinct functions. X is one function, ln x is a second function. So the derivative, remember, the product rule, derivative of the first times the second, plus the first times the derivative of the second. So the derivative of x is just 1 times ln x plus x times the derivative of ln x, which is 1 over x. Now, if you notice here, we have x times 1 over x, which really would be x over x, which is just equal to 1. So we're going to rewrite this and substitute that in. So we have 1 over y equals dy, 1 over y times dy dx is equal to ln of x plus 1. Okay, so now that we've done that, and we've taken the derivative of both sides, we're going to move the y over by multiplying on both sides. So if I want to, just remember back to grade 9, inverse operations, if I want to get rid of a divided by y, I'm going to multiply by y, which means I have to multiply by y on both sides. That eliminates that. So we are left with the derivative of y as it compares to x is equal to y times ln x plus 1. Now, remember back to way up here, we know that y is equal to x raised to the power of x. So we can now substitute that back in for our y value. So we end up with the derivative of y equals x to the power of x, substituting x to the power of x for y, x to the power of x times ln x plus 1. So that's the most simple case of this. We're going to take a look at a couple of examples, and I'm going to show you how we can use this to make regular product rule and quotient rule a little bit easier. Okay, so here is an example. Let's take the derivative or determine the derivative of y equals x minus 1 to the power of 4 times 2x plus 3 to the power of 5 times x squared minus 2x plus 3 to the power of 3. And we're going to look at this two different ways. We're going to start by doing it using the product rule that we know, and then we're going to use our new method of logarithmic differentiation and see how the two compare to each other. So to set this up, we need more space. So I have gone ahead and set this up on a separate piece of paper. So like we did when we were doing the product rule, we're going to divide this out into three separate functions, f, g, and h. And we're going to say, remember our product rule. So this is our product rule. We have the derivative of the first times the second and the third, plus the first times the derivative of the second times the third, plus the first times the second times this is the derivative of the third. So we've just gone down the chain, and we're taking the derivative of one at a time and multiplying them by the regular function of the other two, and then adding them all together. So to help us set this up a little bit, let's start by just writing down what we know. So we know that our function that we've called f is x minus 1 to the power of 4. So the derivative of x minus 1 to the power of 4, now we've got that power rule. I'm going to bring the power down in front. The inside stays the same, reduce the power by 1, and then multiply it by the derivative of the inside. So that's our derivative of f. Now we've got the function g, and our function g is 2x plus 3 raised to the power of 5. Again, we're going to use that power rule, chain rule. So the derivative of this function, bring the power down, 2x plus 3, reduce the power by 1, and now multiply that by the derivative of what's on the inside. The derivative of 2x plus 3 is just 2. So we're going to go ahead and simplify this a little bit because I can multiply those two numbers together. So I get 10 times 2x plus 3 to the power of 4. One more to go, and then we're going to start putting it together. So our function that we've called h is x squared minus 2x plus 3 to the power of 3. Again, we're going to use that chain rule. We're going to bring the power down. So the derivative of h will bring the power down 3 times. What's on the inside? X squared minus 2x plus 3 raised to, we're going to reduce that power by 1, all times the derivative of what's on the inside. So the derivative of x squared is 2x. The derivative of negative 2x is just negative 2, and the derivative of 3 is 0. So now we're going to go ahead and put it all back together like this. So my derivative is going to be equal to the derivative of my first times the other two. So we are going to have derivative of f. So f prime is 4 times x minus 1 cubed times 2x plus 3 to the power of 5. That's my g. Times my f, which is x squared minus 2x plus 3, all raised to the power of 3. Whew. Plus, we're not done. Now we got to do this one. Plus, we have my first, which is x minus 1 cubed, times the derivative of my second one, which was 10. 2x plus 3 to the power of 4 times my third one, x squared minus 2x plus 3, all raised to the power of 3, plus my first one, x minus 1 to the power of 4 times 2x plus 3 to the power of 5 times the derivative of the last one, which was 3x squared minus 2x plus 3 squared. I got to scooch over here a little bit, times 2x minus 2. Okay, there you go. That's it. Now go ahead and simplify. Good luck. It is going to be way easier using ln to be able to differentiate this. And that's what I'm going to show you how to do that right now. Okay, so now let's look at it using logarithmic differentiation. So to do this, we're going to start by taking the ln of both sides. So we will have ln of y is equal to, and I'm just going to throw some square brackets around there, ln of all of our function put together. I want you at this point to remember the product log rule, because the product log rule tells me that if I have 3 terms multiplied together with a ln out in front, that is the same as taking the ln of each one and adding it together, similar to our product rule that we use for differentiation. So ln of y, or the natural logarithm of y, is going to be equal to ln of x minus 1 to the power of 4 plus the ln of 2x plus 3 to the power of 5 plus the ln of x squared minus 2x plus 3 to the power of 3. Now we can bring that power down in front. So it's a little bit of work initially to get it all set up, but then once it's set up, it does make things a little bit easier to take the derivatives. So we're going to bring the powers down. So we end up with 4 ln x minus 1 plus 5 ln 2x plus 3 plus 3 ln x squared minus 2x plus 3. Now we're going to take the derivative of both sides. So the derivative of ln y, remember, is just 1 over y times dy dx. And that's going to equal, now, for each one of these, x minus 1, 2x plus 3, x squared minus 2x plus 3, remember, the derivatives of those is just 1 over the original function. So if we have 1 over the original function, we are going to have 4 times 1 over x minus 1 plus 5 times, now we have to take the derivative of the inside. Sorry, I kind of misspoke there. So the derivative of ln x minus 1 is the derivative of the inside, which is 1, all over the inside. So 1 over x minus 1. So when we take the derivative of ln 2x plus 3, we are going to have the derivative of 2x plus 3, which we know is 2, all over the original, 2x plus 3. And then the final one will be 3 times, now, the derivative of the inside of this, 2x minus 2, all over the original, x squared minus 2x plus 3. Okay, this is looking a little bit better and a little bit easier to deal with. So now we are going to distribute the number in front to inside the bracket. So we still have our 1 over y times dy dx, and we end up with 4 over x minus 1 plus 10 over 2x plus 3. Now, with the 3, we have to distribute it into both terms, so we end up with 6x minus 6 all over x squared minus 2x plus 3. Okay. So now let's move this y so that we are isolating the dy dx. And to do that, we are going to multiply both sides by y. And I'm going to put that y in the front because I know that that's where it ultimately is going to need to go, is in the front. So when we finish with all of that, our derivative, dy dx, is equal to y times 4 over x minus 1 plus 10 over 2x plus 3 plus 6x minus 6 all over x squared minus 2x plus 3. So now all that's left to do is substitute our original equation of y back into where we have y in our equation. Once we've substituted y back in, as I've gone ahead and written out here, we can be done. You may be thinking that we probably should expand and simplify, but I'm going to say in this case, the only time we would really need to do that would be if it was easy to do it. If we have an example like this, where it's not so obviously easy to expand and simplify, we can leave the derivative exactly as it appears here. Let's look at one last example, this time what would traditionally be the quotient rule. So we're going to use the same process here. We're going to use this implicit logarithmic differentiation, which just means we're going to take the ln of both sides and then take the derivative of both sides. So let's take a look at what we have here. So we have y equals e to the x times the root of x squared plus 1 all over x plus 1 times x squared plus 3 to the power of 3. We're going to use the log division rule, which is similar to, not really, we're going to use the log division rule. I was going to try and say it's similar to our quotient rule, but it isn't really. What we're going to do is we are going to take the top and subtract it from the natural logarithm of what's on the bottom. So let's go ahead and let's start doing that. So I'm just going to make this a little bit bigger. So we've already got it set to y. So we are going to take the natural logarithm of both sides. So ln y is equal to, so now e to the x, we have this e to the x. If I take the ln of e to the x, that just becomes, so ln of e to the x just becomes x ln e plus, so we're using a little bit of the product rule here. So derivative of the first times the second plus, now we're going to take the derivative of the next part. So we're going to take the root of x squared plus 1. And I want you to remember that if I have a square root, and this is x squared plus 1, that is the same as making it x squared plus 1 to the power of 1/2. And we're going to do that for this one, just to make it power rule and not having to worry about that root. So if I take the ln of that, I can bring the power down. 1/2 ln of x squared plus 1. Now I'm going to subtract the ln of what's on the bottom. So we take the ln of x plus 1. No need to bring the power down. It's just a power of 1 minus 3 times ln of x squared plus 3. And now we're going to, I'm going to pause because my dog is having 10 fits and I'll be right back. Okay, so now that my dog has sorted himself out, we can go ahead and finish this question. So now I'm going to take the derivative of both sides. So remember, the derivative of ln y is just 1 over y times dy dx. So this is the derivative of y as it relates to x. And I'm going to go ahead, and we know that we have to multiply this by y to bring this y over to the other side. So I am going to kind of skip that step just to save a little time, or a little space actually. But all that I've done here is now I'm multiplying both sides by y, and I'm just going to rewrite it. So now we are left with the derivative of y as it relates to x is all equal to y times, now we're just going to start taking the derivative. So the derivative of x ln x is just x times 1 over x. The derivative of 1/2, we're going to add that to the derivative of 1/2 ln x squared plus 1. That becomes 1/2 times the derivative of this, which is 2x all over x squared plus 1. Then I'm going to subtract from that my derivative of ln x plus 1. Derivative of ln x plus 1 is just the derivative of it, 1, all over the original x plus 1. Now I'm going to take the derivative of the last one. 3 ln x squared plus 3 is going to be 3 times the derivative of this, which is 2x, all over x plus 3. Now what I'm going to do is I'm going to go in and I'm going to see, is there any place that I can simplify a little bit or cross things out? Is there anywhere that I can eliminate things? And there is. This 2 on the top of here can eliminate that 2 there. That gets rid of a fraction. So now we're going to go ahead, we're going to go in and we're going to simplify a little bit. So we have dy over dx is equal to our original function y. So now we have x over x, which is just equal to 1. So that's 1 plus our next bit, which is our x over x squared plus 2, or x squared plus 1, minus 1 over x plus 1. Now I'm going to go ahead and I'm going to multiply that 3 in. So that's minus 6x over x plus 3. Now we're going to go ahead and fill our original function back in there. So our derivative of dy as it relates to dx, or the derivative of this function, is going to be equal to e to the x root of x squared plus 1 all over x plus 1 times x squared plus 3 to the power of 3 times 1 plus x over x squared plus 1 minus 1 over x plus 1 minus 6x over x plus 3. So that's using our natural logarithm and some implicit differentiation to determine the derivative of product rule. So we had product rule, we had quotient rule, what we normally would have quotient rule, and doing it in a little bit more of an efficient manner. Again, I'm not going to expand this out. I'm not going to expand that into there because at this point there's really no need for us to do that. And we can just leave it as it is. If you're just trying to find the derivative, this is the derivative. Okay, so I have posted to the VLE a handout that has some questions on it. The solutions or the answers are there as well. Take some time to go ahead and take a look at that. And if you have any questions, feel free to email me.